Here we continuously look at the shear and bending moment diagram, and this is the second approach for drawing the shear and bending moment diagram. This approach is what I preferred over the previous method, and that talk we discussed in the previous sections. Basically, here is start with the relationship between the V M and the distributed loading W. So we see here. So we consider a beam is under a general form of the distributed loading W, and which is a function of X. And here showing is very general. And so from here, if we take only a small portions as a free body diagram, and then we analyze the given loading as the distributed. And then here we take in the free body diagram and to find out on this end is the shear, and this is shear V plus delta V as small incremental change, and due to the external loading here, and again the M and bending moment M plus a small incremental change. So from here, those small incremental change in V and M over this the size delta X, then we take in the equilibrium equation. Actually, we will lead to two important equations: dV dx equal to minus W, dm dx equal to V. Basically, this is saying that the slope of V, the slope in the curve of the shear diagram equal to the value of the minus omega at that positions. And here for the sign convention, here I want to emphasize the sign convention for W is positive downward as we formulated here. Okay, this is a sign convention for W. Memorize this, please. And then the second equation here, dm dx equal to V, simply saying that the slope in the bending moment curve equal to the value of the V at that positions. So here we're going to, based upon the two important equations, we're going to try to see how that can be applied to help us draw the shear and bending moment diagram. So that's the first point. The second point is about this. We derive from these differential expressions. If we take the integral on the both sides and over, say, 2 points from X, from the position here to here, okay, that called the position XC to here, that is a position called the XD, measured from point A here. This is XD, and this is XC. So if we do the integral, then basically that's saying the difference of VD and VC equal to this one. Similarly, we take the integral, then the difference of the moment equal to this integral. And what this means, I'm going to explain this in detail. Excuse me. So let's take a look at in more details about how to apply these equations and what this means here. So before we doing this, again, you need to pick up another sign convention for distributed loading W, and put downward as a positive. If there's any loading distributed loading upward, then that you take the negative sign here. Okay, so now I'm going to explain what this means here. Okay, this simply means the difference between VC and VD. So for example, we consider two locations, and one is at this location. Let me change the color of the pen. So one location is here, the other location is here. Okay, we'll look at the two locations. And assuming we know the value of the location as C equal to VC here, and then we want to know the location of VD. Okay, the value of the VD, basically VD equal to the shear force is decreased. Basically, this meaning is the decrease, the shear force decrease from VC to VD. That decreasing is equal to the area under the W curve. So basically, this is the curve in this segment we're interested. Okay, so this is the area. If you are able to calculate this area, let me call A. Okay, let me call this area equal to A. So basically, in this way, this decreased amount is A here. Okay, so this area equal to A, and that decreasing is from VC to VD by amount of A, by the amount of the area underneath the W curve. That is the meaning of this integration here. And how about this? And we look at another equation, dm dx equal to v, and we have this one, and similar concept. Again, the difference between the two moments equal to the area under the v here. So we'll look at this example here. So for example, let me say this is a position 1, and this is a position 2, okay? And we know at the beginning, at this point, there's no any bending moment applied, so start at 0 here. So that means this is the bending M1 equal to 0 here. Okay, that's a position 1. And now I want to look for the value of the M2. Then I simply put into this equation M2 minus M1 equal to this. What is this? This is the area under the V versus X curve. Okay. So here, for example, here that this is the area enclosed by the V, the shear force curve. Okay. So M2 M minus M1 equal to that amount. And here, when we applied here, you can see I put a sign here. For those area above the horizontal axis that defined as the positive value, the area underneath has a negative value. So for this case, basically this area is negative. For example, say this area is 20. Say, let me say the distance here from here is, I just make it up. Okay, for example, if this is 2 meters here, so then this area, which is below the horizontal axis, in magnitude equal to 20 kilonewton multiplied with 2 meters. This is the magnitude because here per our sign this is negative. So therefore M2 minus M1 equal to the area under the curve, and here we calculated minus 40 kilonewtons meter. Okay, so that means M2 equal to M1 minus 40 kilonewtons meter, and M1 equal to 0 as we indicated here. So this is the M2 here. M2 value equal to minus 40. Okay, so for example here, if I take the unit kilonewton meter here, okay. So we can continue. So for example here, we can continue at this position. There's a point 3. So point 3 in a similar way, let me say the point 3, this is the M3 here. So that is the value of the M3 here. Okay. So now, for example, if I want to calculate, say, the point here, that point is M4. So same, let me assume the distance between 3 and 4, say 3 meters. Okay. So in this way, this area between the 3 and 4, again, that is the area under the curve, under the Vx, the shear diagram curve between position 3 and position 4. That is this area. So this area has the magnitude equal to 26, that's the magnitude 26 kilonewton multiplied with 3 meters. So that equal to 78 kilonewtons meter. This is the magnitude, and this area is above the horizontal axis. So basically that is a positive. Okay. Okay. Now from here, then we plug into this equation, into this pattern of the equation is M3. So no, M4 minus M3 equal to the area under this curve, which equal to 78. So M4 equal to M3 plus 78. So if we have previously determined the M3 value is here, you simply move upward by amount of the 78 here. Okay, so from here to here, you move upward by 78. This is the value of the M4. Okay, so that is the value of the M4 here. So by doing this kind of illustrating this kind of the equation here. Okay, so we can apply the dv dx equal to minus w, and then dm and dx equal to v. Okay, so let me do this one. dv dx equal to minus w. So we see. So for these questions, we still want to construct the shear diagram, bending moment diagram. We start from here. So from the beginning here, that is the 20 here is our sign, positive, and this is the positive shear. Okay, so for this case, you can see this is a face left, and we have the 20 downward. Per our sign convention, that is negative. So starting from here, negative. Let me change color here. So starting from here is negative 20 and corresponding to the load here. Okay. And now from here we look at here in between this segment. In this segment, there's a no distributed loading. So in this segment, omega equal to 0. So that means omega equal to 0, no distributed loading. Omega equal to 0, so that means V equal to constant. And also we know V start from minus 20, so that is remain as constant in this segment here. Now we come to the point where the 0.6 point upward. So that 0.6 will 46 will put upward from current value upward by 46 to here positive 26 here. Okay, and now again in this segment there's a no distributed loading, so dv dx equal to 0, which means v equal to constant, and also v is constant remain as 26. So here in this segment is 26. Then down to here is a force pointing down 40. So from here we move in the same sense to 40 here. So from 46, so from 26 move downward by 40. So that is 14. Okay. So basically this distance is by 40. Okay, as the downward by this. And again, in this segment, there's a no distributed loading, so dv dx equal to 0, and then v equal to constant and remain as minus 14. So that is the shear diagram. So you can see from here is this method combining with these equations, and together with the, I would say, boundary conditions at a few locations, that kind of makes things easier. Now we look at the diagram, the bending diagram here. Okay, the bending diagram we look at from the boundary here. At this free end, left hand side, there's a no bending, so we start from 0 here. Okay, and now we proceed the bending. So in the first segment, dm dx equal to v, so dm dx equal to v. What is v? V in this case is minus 20, constant. Oh, that's super nice, because that one gives us these things. We know that dm dx equal to constant slope, and constant slope negative constant slope, so we can say that's a straight line like this. I like this form. Okay, so this is minus 20 here. And now to proceed, you need to calculate where it ends. So 20 multiplied with this distance and 2.5, so it ends up as minus 50 here. Okay, so you need to know where that will start for the second segment here. Okay, and now for the second segment, and again in this segment here, let me change color of my pen. In the second segment, again we still have this property dm dx equal to v. And in this second segment, the v has the constant value equal to positive 26. So that means in this segment that has the straight line as well. And now in this case is a positive slope, and the slope equal to 26. So this is a slope 26. Again, that is a straight line, but with the positive slope like this. And now for this case, we need to calculate how much it increased from here to here. So I want to know how much it increased. So this value can be easily calculated by 26 multiplied with this distance. How much? 3. Okay, so that is 78. So from minus 50 increase by 78, so this end up to here, this is the value is 28. Okay. So the m, the moment at this point, at this location is equal to 28. That serves as the starting point of our last work. So the last work, let me use this color here. Okay, again, right now I'm looking at in this segment, and again in that segment, dm dx equal to v. Again, in this segment, the v equal to constant minus 14. Oh, super nice, another straight line. The straight line will be a slope, negative slope, okay, with the minus 14. And then we also expecting the, because this free end here has no moment, so this line should meet here. Okay, so this will provide you a check. If you somehow, for some reason, if your drawing of the last line, the last segment of the line couldn't meet here, then that indicating something going on, something going wrong here in your previous drawing. So go back to check your calculation. So again, that will provide you kind of the tip for this. And here is the answer from the previous exercise here. And if you necessary, you can rewind a few minutes back and to rewatch this portion here. But here, let me move on. So here, let us look at another example here. This is the continuously constant distributed loading. And again, for this case, the W is downward, so those are the positive. Okay, those W are positive per our sign convention. So for this case, again, for drawing the shear bending moment diagram, the first step is always to find the direction here. Okay, so assuming you know how to do it, direction on the both sides is this one. So basically, this is our starting point of drawing. So that is the force here, okay, and that is a force here. So now we applied the two equations, and from V here we're starting at this free end. There's no shear force, so starting from 0 here. No, sorry, at this end we simply calculated the force is Ra equal to this one, so we should start from here. That value equal to 1/2 and omega L. Okay, we start from here, not from there. Let me erase this one. Okay, and now in this segment, the dv and dx equal to minus omega, and here the omega is a constant. Omega is a constant value. How about this? Let me call this is omega 0 to make that more generic. Okay, and this omega 0, that is a value, and per our sign conventions, and the downward is positive. Okay, so negative, and this is a constant omega 0 per sign convention. So basically that is the this one here. So you can see dv dx equal to a constant equal to a negative constant. That means the slope equal to constant. So that means when we draw that one, the thing should be something like this. We keep a straight line as the slope with the slope equal to minus omega 0 here. Okay, so this is omega 0. So then it passing through, sorry, my drawing is not so perfect, but it's passing through 0, intersecting with the horizontal axis at the middle of the beam here. Okay, and then ending up here is minus 1/2 omega 0 alpha L. And then we have done this one. Then we move on to the m of x, and then let me change color for m of x. So let me say using this color here. Okay, so in this segment here, and you can see in this diagram there's a no bending, so we expect the bending starting from 0. At the end B, there's a no bending, so we expect the ending should end up at 0 here. So now we're going to figure out the in between. Okay, so there's two ways you can try, and the first way is the dm dx equal to v, and v is a function of x. You can start from here, and what is a vx? You simply formulate this equation here. For this equation, that's a straight line, and the straight line starting at 1/2 omega 0, and with the negative slope. So this is the equation here. Okay, so this one is minus omega 0x plus 1/2 and omega 0L. So you're doing the integral here. So basically m should be equal to minus omega and x over 2 square plus 1/2 omega 0Lx and plus certain integration constant. Let me call integration constant, say alpha here. And alpha can be determined by the boundary conditions. For example, at x equal to 0, m equal to 0. So from there, we know alpha must be equal to 0. So this is the equation for m of x. Okay. So if you would plot this one, then that would be something like this. Okay, if you plot it correctly, so that would be something like this. And basically that is the parabolic curve, and the max happen at the middle here. Okay, so this is parabolic. Okay, so that is the where is the form? Okay, so that is the detailed calculation for this example here. Okay, and you can look at this one. And here I want to, by taking this opportunity, to introduce you another way to directly draw the bending diagram. And here let me use the different color here, okay, for demonstration using green color. Again, from here we're expecting the bending start at 0, ending up at the 0 value here. Okay, and now for this drawing, I'm going to stick with the dm and dx equal to v. Okay, we'll look at here. That means the slope of the bending curve, the curve we're going to draw, the slope of the bending curve equal to the value of v. And how do that say? Okay, we start from here. So let me say, pick a few points. Okay, so let me select a few points here, few locations. So here I'm going to do this, the drawing here, the drawing here, drawing here, 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 here. Okay, I'm going to demonstrate the drawing at those locations. Oops. So at 0 here, the value, the slope of m curve equal to v, and v is equal to that big, the maximum. So the slope equal, kind of schematically is that big. Okay, and that big we can schematically say that one proceeding to here, and then to this point at these locations, then the value of the v decreasing a little bit. So that means at this point the slope is decreased a little bit but still remain positive. Then we proceed to this location here, then the v even smaller but still positive. So at this location here, the slope even smaller, which means not that deep, not that steep. Okay, so now to this location here, the v even smaller but still keep positive. So at this location is even getting flat. Okay, so you can see when we progress, and then this kind of slope kind of getting flat and flatter until approaching to this point here, the v equal to 0. So that means here the slope equal to 0. That means it's horizontal here. Okay, so for this case, if you trace those kind of tendency, then you can see that kind of the basically forming is this kind of things here. And then we trace the dv at this position. At this position, v equal to a little bit a small negative. So the small negative at this position, at this location here, the slope is little small negative. So that can be flat but downward. And at these locations, the v equal more negative. So at this point, here, the slope equal to more negative, and this point is even more negative and more negative. So basically, you trace the things, and you eventually will kind of schematically show for yourself, and that is the curve for bending. And this is a very fast approach, and based upon simply directly observing the geometric information provided by the problem here. But this approach is built up upon the total understanding of the two equations. So I would say my suggestion is this: before you get familiar with it with the all detailed, you know how to do the detailed calculations, say for example by integrating the integration, something like this one. Before you have a thorough exercise, then you can proceed this kind of very direct graphical the method. Okay, so this is the solution here again. For this case, this is the solution here in the next slides. Okay, so this one can provide for your self-reference, and basically here this information you have to divide your calculation in two segments. This segment AB and the segment BC. Okay, so you need to deal with your calculations piecewise and for individual segment. Okay, and the calculation shouldn't be hard, and it's very straightforward integration. And once you have the curve expression of the curve, you simply draw the curve. Okay, and for this case, this is the equation here. You simply draw the curve. Okay, and if necessary, you can have the grid paper, the paper printed with grid, and draw those on the papers there. Okay, and then for, let me see, for this segment, and again you have this value that's a constant, so you can draw this line, and for bending you can make this line here. Okay, and this is our textbook example, and this example should be very straightforward. Maybe I can do the final demonstration here. Okay, so for here we start from the build up the bending, the shear diagram using this formula here. So from this point and at this here, they're starting at 18. Okay, and the unit is the 1,000 pounds. So 18, and here in this segment there's a no distributed loading, so dV dx equal to minus W, and in this segment equal to 0, so keep as a constant. And now to point B, where there's a loading 20 downward applied, so that will decrease by 20, so from 18 to minus 2 here. Okay, so the amount is 20. From here to here, amount is 20. And this 20 is caused by this. Okay, and now again in this segment, no distributed loading, so dV dx still equal to 0, so keep going as a constant. Now to here, expecting, and again downward by 12, so from minus 2 to minus 14. Okay, then again in this segment, no distributed loading, keep constant. And now to here, we have the point loading 26, so that will move from minus 14 to 12. Okay, and now in this segment here, we have the distributed loading dV dx equal to minus W equal to minus 1.5. Okay, so that one will have a slope, and this slope is minus 1.5. And to this moment, your drawing should end at 0 here, because here we don't have any shear force here, so must end at here. So now it's providing you to check. So if everything so far is correct, then this straight line with negative slope of minus 0.5, then you will have that line when progress this distance, they must meet here, and that should be there. So that provides you a check. Now we draw the bending diagram. So bending diagram, again, we look at this original at the two ends, they no bending, so we should start from 0, ended up at 0 here. Okay, and now in this segment, the dm and dx equal to v. So in the first segment, the v equal to 18, constant, so remain as a constant. The slope equal to 18. And then we can calculate the end value. So 18 multiplied with this distance, this is 6 feet. Okay, so that is 108 m at this value here. Okay, and then we change color to the next one. So the next one, again, the dm and dx equal to v, and here the v equal to -2 in this segment, okay, -2 here. So that is a slope, a straight line with the negative slope -2. So its ending will be from here, 108 to how much? The distance here is 8 feet. So 8 feet get a descent by 12. So -2 times 8 equal to -16. 108 minus 16 equal to how much? 92. Okay. So here the value, m. Sorry, let me. So m here equal to 92 here. Okay, and then we move on to the next segment. In the next segment, again, the dm and dx equal to v, and in this segment here, this is -14 constant, so even have a -14. Okay, so here my drawing is not so perfect, but the slope is -14 here. Okay, and here the distance here is 10 feet. So here right now we descend from 92 by how much? By 140. So that is go to 140, 90 to 140, and to minus m equal to -48. So the value here, m equal to -48. Okay, and then to this one, then in the final segment, which color I have not used, okay, red one. In the final segment, the dm is the controlling the pen is not so perfect here. Okay, sorry. So in the final, the dm and dx and equal to v. Right now you can see the v is the decreasing. So basically here we can say at this point the slope is 12. Okay, that kind of big. And then to this position, the slope equal to a little bit less positive, so that is less negative. So basically in the final segment, that should be kind of the portion of the parabolic, something like this. So this one, schematically, this is a parabolic. Okay, parabolic shape. And then approaching to 0 here, and the tangent. At the final point here, because v becomes 0, so the slope equal to 0, so that means this parabolic curve must tangent at the end point there. Okay, so that is the kind of schematic drawing of the things. And for exercise, in terms of the homework assignments and the testing, it's important to get the correct the point. To get the point is this: I simply want you to mark the featured points, which means the turn point here. What is the value here? For example, you need to give me this number, and then here, for example, here, what is this value here? You need to give me this number. And then what is the turn point here? You need to give me this number, and then in addition to the slope. Okay, so those are what I mean, the feature point. And even better, if you can indicate this is a parabolic curve in this kind of the curve segment here, that'll be even better here. Okay, and the same thing for gradient purpose. I'm looking into here. I'm looking into will be this value will be correct. This value, and this value, and even this slope here. Okay, I'm looking into those kind of the feature things and to give the gradient of this kind of problem. Okay, so that is the detailed calculation for your reference.